തുടങ്ങാം. നിങ്ങൾക്കെല്ലാം പിന്നെ പോയി പഠിക്കാനില്ലേ?
Yes, sir. തുടങ്ങാം.
Yes, sir. Okay. So today we will see some of the topics that we have not covered in our regular thing. It's good to know about these things. Okay. Can you differentiate between these two cycles?
Yes, sir.
In the cycle,
Sir, open and close.
open cycle, close stable. ഇത് രണ്ടും നമ്മൾ കണ്ടിരുന്നല്ലേ?
Yes, sir.
Right. Okay. Now we need to differentiate between this. Sometimes it is asked, differentiate between or give the difference between open cycle and closed cycle. Other than the configuration, you may have to write some more points. Okay. So if we can see advantages and disadvantages, we can write, even the question is like that. And also we can write if the differences are asked. Okay. So this is the advantages of closed cycle over open cycle. The first advantage is you can see that when it is closed one, we can go for very high pressures. Okay. If it is very high pressure, that the density of the air would be more. If the density is more, then the mass would be more, because for the in the same volume, more molecules will be there. So you know that all the equations you have to multiply with mass, not with the volume. So if higher the pressure, we are handling more mass. If you are handling more mass, the work output would be more, because m is multiplied. So higher pressure. Then even if the load varies, okay, we can change by monitoring, altering the pressure level, and without much affecting the, because it's a heat exchanger. You can see that in closed cycle, it is a heat exchanger. Here it is the combustion. Here it is an heat exchanger. So these temperatures you can control actually. Here you don't have any control. The amount of fuel which puts in and the burning, the combustion actually determines what is the temperature. But here you have more control of the temperature, and you can play with the compressor pressure outlet to take care of this load, generator load. So it's more fluctuation, friendly, the closed cycle. The major advantage is this corrosion and erosion of the turbine blades. You know that in this cycle actually determines what is the temperature. But here you have more control of the temperature, with the turbine, and you can play with the compressor pressure outlets to take care of this load, generator load, corrode. So it's more one of the major fluctuations in open cycle is the maintenance of the turbine blades and its housing and things like that. So if it is closed cycle, the products of combustion is going back. So it is not coming into, there is only a fluid, generally helium or something, which will be heated, and that hot fluid only come in contact with the turbine blades, where the product of combustion comes in and goes out. So it's not in contact with the turbine blade. So there are more life for this turbine blades in case of closed cycle. Right. Then it says that filtration of the working fluid is not required except charging for the first time, because here you can see that it's a closed cycle. You are not allowing any new thing to come in. So at the start of the process, you need to admit some helium gas, but here in case each time the atmospheric air is taken, you need to take care that the dust is not there, and water vapor is not there. A lot of things we have to avoid in filter at the inlet, so that each time it has to be done. Then the filters will get clogged and things like that. So closed cycle doesn't have that problem, because it is a closed one and the same fluid is rotating. High density working fluid improves heat transfer, helps to improve the effectiveness of the heat exchanger. The size of the compressor turbine actually can be reduced. That says Here you need to select some fluid such that combustion will happen. So basically, having oxygen is something which is important in this case. But in closed cycle, you don't have such requirements. You can go for a denser fluid here because it is not getting burned and all. So any fluid will work. So if the fluid density is high, your compressor can work. Work of compressor can be less. The size of the heat exchanger can be less. The turbine with a smaller size can produce the same work which it produces otherwise. Here also the heat exchanger can be small. So here we can use only air or oxygen as the fluid because you want combustion to happen. Right? Are you following?
Yes, sir.
Right. Then it says solid fuel can be used more economically under indirect. For example, you wanted to burn coal, okay, coal or wood or something, then you can't do it in this system because it is not possible. You need to have some sort of a spraying fuel or a gaseous fuel that comes into the combustion chamber, then it burns. But here you can use coal or something which is it is burned outside, so it is nothing to do with the fluid. So we can use because in a system like India where we don't have much petroleum based fuels, this coal based ones are more practical, though it is more polluting. It is not more practical and economical for countries like India where there is abundant source of coal and all, right? So that is uh, can be used more economically as indirect heating is used, okay? But this can't be used in open cycle. Working fluids other than air having better thermodynamic property, helium, can be used in closed cycle. This we have talked. Can use any fluid of our choice, but in open cycle you need to use something which is which has got oxygen in it. Okay. Now there are disadvantages also. Disadvantage, one of the major disadvantages, we need a lot of water for cooling. Okay, you can see in this diagram, this has to be cooled down. Okay, because after you want the recording to be on, hijab says.
Sir,
I don't think you can record it. Can you record?
Sir,
Maybe you can switch on your mobile and record it. Google Meet recording, I don't think it is there. I can share you the PPT. Who is the admin for this? Royce?
like college തരുന്ന ഒരു ഐഡിയ ആയിരുന്നു.
റോയ്സിന്റെ ശബ്ദം ഭയങ്കര ഫീബിൾ ആണ്, എനിക്ക് കേൾക്കാനേ പറ്റുന്നില്ല.
സോറി, ലിങ്ക് ലൈക്ക് കോളേജിൽ നിന്ന് ഉള്ള ലിങ്കാ. അപ്പൊ ലൈക്ക് ആർക്ക് വേണേലും റെക്കോർഡ് ചെയ്യാം എന്നുള്ള സെൻസില്ല. ഐഡിയ ഉള്ളവർക്ക് അങ്ങനെന്തോ.
എനിക്ക് തോന്നുന്നില്ല. Maybe you can switch on your mobile phone and record it. Okay. Shall I continue?
Yes, sir.
Right. So one of the major disadvantages of this closed cycle is this cooling water, because after this expansion of the turbine, the water has to be cooled. Otherwise, the compressor work will be high, because you have already seen, because your compressor work is proportional to the inlet temperature. So you wanted this to be as low as possible so that the compressor work is not very high. Okay. So you need to use some cooling water. So this can be some sea body, some river water or something, which you people used to do earlier, but now it can be done because this will be hot water. You can put that back into the river because it will affect the aquatic life. So maybe we need something like cooling towers and all, so that this water which is coming out is again recirculated, taking into a cooling tower, cooling it back and again giving it. So this requires bigger setups like chillers or cooling water, we call cooling towers and things like that. Okay. So because of the same reason, they are used for stationary plants. They can be used in a flight, because if you say that you need to cool this, you need to carry water in the air, and it's not possible to be used in moving systems. So you need to use something for the electric power production, something where it is a stationary plant, we can use this open cycle. Also, the capacity of the cooler is linearly very large. Air heater compared to combustion chamber, because of this heat transfer coefficient, or this what you call this heat exchanger, is just a heater. So this should be enormous size, so that you have very high temperatures developed at the end than combustion chamber. Combustion chamber can be a smaller one because the heat generator would be high, but here you need to transfer heat from one fluid to the other, and that requires setups which are big. Okay? And for the same reason, the weight of the plant per kilowatt of power produced would be high. Okay, and it is necessary the system must be absolute leak proof in the working fluid. Otherwise, it can be used as a closed cycle, because somewhere the gas leak is there, then it is a problem. But in open cycle, because it's open, even if there is some leak here and there, it can be compensated, because otherwise this pressure will be continuously dropping, and you will not be able to achieve the required temperature and the pressures at the various points. Okay, so these are some of the advantages or disadvantages or differences that you can write about open cycle and closed cycle. Okay, I had a question regarding semi-closed gas turbine cycles, but I couldn't find this in majority of the books, but I could manage it from some places, which I don't think there's a popular one, but if it is asked, you can write. So it's basically a combination of open cycle and closed cycle, as you can see in the diagram. So you can see at the middle, you have something similar to a closed cycle. So you have the compressor, then you have the heater, then it expands in a turbine, and then it is cooled, and then it is fed to the compressor again, and this is coupled. Now in semi-closed cycle, what they do is they will add one more compressor, which they call as the auxiliary compressor, and it is coupled to the same shaft, you can see, and that gives some additional air into the system, so that it's given to the second compressor. This may not be very high pressure, because it becomes an input to the the second compressor. So then the output of the second compressor, you can see, is bypassed. Everything doesn't go into the heater, but it is bypassed, and some air goes into the combustion chamber, where along with the fuel it is burnt. So that part you are expanding it in another turbine, where that power output is also utilized, and that is taken out. So this is a sort of what you call a combination of. So if you see this part, it is closed cycle. If you combine this, it is an open cycle. So this is found in some of the textbooks. If it is if it is asked, you can talk something about that. All right. So whatever this exhaust is giving out, this air will be taking in the same amount, and thus what the mass will be balanced in the system. Is it clear? Should I repeat it again?
Clear, sir.
Clear ആണ്. ഒന്നുകൂടെ പറയണ്ട.
മനസ്സിലായി sir.
Okay. Okay. Now I have also seen a patent which is slightly different from what I have. That is also called as semi-closed gas turbine cycle. So what they do is, instead of doing this open cycle, this gas which is coming out, they treat it. And everything is not given out. A part is given out, like nitrous oxide, carbon monoxide, and such things. Whatever which can be taken out is treated and again fed into the compressor open cycle with some oxygen injection and all. So that is also another cycle, they say. This provided also can be converted into open combined cycle gas turbine into a non-polluting one. So open cycle one is generally a polluting one, so it can be made non-polluting. So what they do is, exhaust is not emitted in the atmosphere with a typical, but rather it is routed to a divider. The divider splits the exhaust into a return duct and a separation duct. So the separation duct, whatever is exhausted, is written that routes a portion of the exhaust back to the compressor. So that's what I said. Some part is given out, some part is sent back to the compressor again. And before reaching the compressor, oxygen is added, so that at the end the combustion is basically you have a gas mixture which is almost like air, but not exactly air, but it is the outcome of the earlier combustion product. So by doing this way, the compressor need not be modified. You can use the same compressor. So this is another type of semi-closed gas turbine cycle I have seen. So I think this would be a better one, because that one probably is this one is probably a new what you call a patent. So this may be a right one. All right. Right. Okay. Can you identify what is this I am showing? Flight engine. It's a flight engine where there are some fans at the start, then there's a compressor, then there's a combustion chamber, then there's a turbine, then you have the hot gases coming out. Okay. Now this we have discussed when we talked about gas turbine cycles, because this is exactly what we do. We have a compressor, we compress it, then we take it to the combustion chamber where it is burned, and then it is expanded in the turbine. So it's basically our gas turbine cycle. Now if you see the temperature, pressure and velocity variation in these cases, you can see that say let us take the pressure in the fan stage. In the initial stage, you can see that the pressure is not much increased, but when it comes to the compressor stage, it is ramping up. Then in combustion chamber, it either remains almost the same or slight pressure drop is there. Then in the turbine, it is expanded, so the pressure drops and it goes out to the excess. Okay. Similarly, you can see the temperature also slightly increases because of the combustion, and also the compression. Combustion will increase it, the fluid temperature. Okay. But the compression also will increase, because that pressure is proportional to temperature. So when you increase the pressure, the temperature also should increase. And then it expands, so the temperature drops and it goes out. Okay. And drops the temperature. Now the velocity, if you see, it almost remains the same till it comes to the combustion chamber before the turbine. So you can see that the fan and all, it is not exactly increasing the velocity as we expect. But what actually happens is the kinetic energy is converted to pressure energy, if we can see, so that the energy is balanced. So the velocity is not exactly increased in the process. Now that is very interesting how they do it. And that type of compressor is the one which we will see today. It looks like this. Okay. This is a structure of that. So there is a drum in the middle and there are some blades. This is a front fan and all. So this you can see it in a flight. So this is exactly I have shown here. So this is the engine. So cut section looks like this. So can you see that it can be opened up? So how they do it? Okay, they have something called axial fork compressor, where basically they are not interested in increasing the velocity. In fact, the velocity remains the same and the pressure is increased. So today we will see how they do it. Okay, in axial fork compressors. So this is a typical axial fork compressor that is used in the flight. So you can see the size. There's a person standing there. It's pretty big. So this is a drum onto which there are some blades. You can see these are the rotor blades. Okay, there are rotor as well as stator there. So you can see that the ones which we see is this one. This is a drum, and these blades, the alternative blades that you can see, that is R1, rotor 1, rotor 2, rotor 3, rotor 4. That is the one which you see here. So in the casing, in the covering of this, there are another set of blades that is the stationary blades. So S1, S2, stationary or stator blade, or they call as a guide blade also. So guide blade is connected to the what you call the casing of this. So once you cover it, it becomes the whole compressor. Okay. Now it rotates like this. I don't know whether you can see that animation.
Yes, sir.
Right. So only the rotor rotates, and the stator, you can see they are stationary, they are not moving. They are, this is the inlet and this is the exit, the outlet. So these blades, all the blades are moving at the same speed. Okay. But interestingly, you can see that the center part of this drum is actually increasing in size when it goes from inlet to outlet. Say for example here, this is the diameter of the drum. When it goes to the this part, the diameter increases. So what actually happens is the space decreases. Okay. So this actually makes the velocity constant. If this is also having the same size blades, then the velocity will increase. So what they are trying to do is they are converting the kinetic energy into pressure energy in this case. Okay. So these are the typical rotor blades, okay, like a drum, and these are aerofoil shapes. Okay, they are shaped as an aerofoil. Now it consists of adjacent rows of moving blades, that is called rotor blades, and fixed blades on the casing, that is called the stator blades. Rows of moving are mounted on a rotating drum, it's called the rotor, and rows of fixed blade are fixed on the casing of the compressor. The pair, one moving blade and one fixed blade, is called as a stage. Okay. Generally, this is small compression, like 1 to 1.2, 1.2, 1.3. That is the increase in pressure ratio in one stage. So these are generally multi-stage compressors, minimum 5 stage. There can be 12, 13, 14 stages, so that you can have, we can go for higher pressure ratios. So the outlet of the first stage becomes the inlet to the next stage, and so on and so forth. There is no cooling like the earlier multi-stage that we have seen. These are rows of, or sets of rotor and stator, attached to one by one. Okay. So, and each one is called a stage. So generally multi-compressor, it can go up to 1.2 to 1.3 per stage. So you can have 8 stage for it. You can have high pressures. Okay. So suitable for high pressure ratio. The annular area of the airflow is gradually reduced from the inlet to the outlet of the compressor so that the air velocity is constant. So this is how they do it. Generally more efficient than the centrifugal compressor, most cases. They are widely used in gas turbine plants, more power plants, also in blast furnace, air separation, cryogenic air separation plants, then propane dehydrogenation plants, and also there is something called supercharger. I don't know whether you heard, in especially in lorries and all, there is something called supercharger. എസ് ഐക്കാരെങ്കിലും ഉണ്ടോ? സൂപ്പർ ചാർജർ എന്താണെന്നറിയോ? ടർബോ ചാർജർ അറിയോ? ടർബോ കാറിനകത്ത് ടർബോ ഉണ്ട്, ടർബോ ചാർജർ ഉണ്ട്.
സർ എയർ ഇൻടേക്ക് കൂട്ടാനായിട്ട് യൂസ് ചെയ്യുന്നതാണ്.
എയർ
ഇൻടേക്ക് കൂട്ടാനായിട്ട് ഇപ്പോൾ കമ്പഷൻ.
എക്സാക്ട്ലി, എയർ ഇൻടേക്ക് കൂട്ടും. നമ്മൾ പുറത്തുനിന്ന് സക്ക് ചെയ്യുമ്പം ജനറലി സക്ഷൻ സ്ട്രോക്കിൽ അറ്റ്മോസ്ഫിയറിക് എയറേ കയറത്തുള്ളൂ. സോ വാട്ട് ദേ ഡു ഇസ്, ഒരു ചെറിയ കംപ്രസർ സെക്ഷൻ സൈഡിൽ കൊടുത്തിട്ട് സക്ക് ചെയ്യുമ്പം കംപ്രസ്ഡ് എയർ കയറാനായിട്ട് ചെയ്യും. ദെൻ ഇറ്റ് ഈസ് കോൾഡ് സൂപ്പർ ചാർജ്. സോ ബേസിക്കലി യു ഹാവ് മോർ പവർ ഡെവലപ്ഡ് because you multiply with the mass flow rate, so you are handling more mass, so your combustion combustion pressure will be more, and you are getting more work done. So that's called supercharger. Turbocharger എന്ന് പറഞ്ഞാൽ എക്സാക്ട്ലി എക്സോസ്റ്റ് ഗ്യാസ് എടുത്തിട്ട് അതിൻ്റെ പ്രഷർ വെച്ചിട്ട് ഒരു ടർബൈൻ കറക്കി അതിൻ്റെ ഔട്ട്പുട്ട് എടുത്ത് എഞ്ചിനിൽ കൊടുക്കുമ്പോഴാണ്, ബേസിക്കലി ഫോർ മോർ പവർ, again for more power. But one is done at the suction side, one is done at the exhaust side. Okay. Supercharger usually heavy vehicles, lorry, bus, big trucks and all, they do it. Okay. So there they use this axial flow compressors. GK. Okay. So this is what I said. You can see that the area is reduced. Now let's come back to our problem. Okay. We need to draw the velocity triangle and find out what is the work required for this compressor. So to do that, we can see that there are an array of blades, like I have shown. There are an array of blades like this. You have an array of blades. Blade two. This is the stator. Below this, you will have this is a rotor. Below this, you have the stator. So each one will have array of aerofoils. So that's what it is shown here. And this is the axial direction. Okay, that is the axis of the rotor is in this direction. The blade is rotating in this direction. So U. So at this end, this is the inlet. This is the outlet. So this direction it is U1 and this is this end it is U2 if you wanted to do it. Okay. Now let's see how the velocity triangle is made. Okay. Can anyone tell me? Velocity triangle not the expert sign and I am another. Logically, Parisha, any expert expert You want me to explain this?
Yes, sir.
Okay. I said this is the axial direction, that B to C. So from the axial direction, it makes an angle alpha. The inlet air comes with some velocity V1. Okay. So it comes here. Okay. It comes here like this. It is making an angle alpha with the axis. Now this end, I said the blade is moving in this direction. So this end, it is moving in U1. So that U1 is marked here. So this the whole thing is from A to D is U1. And to that, because of that, and this is V1. So you have a relative velocity VR1. Okay. So U1, V1, and connecting both, we have an velocity VR1. Okay. This V1 we can derive, we can resolve into the flow component as well as the whirl component. So this would be your VF1 and this would be your VW2, VW1, the inlet whirl component. And the angle that this VR2 makes is nothing but your theta. Clear? I repeat, the air is coming with an angle alpha with the axis of the rotor. This is V1. And the blade, the tip of the blade at this side is moving with a velocity U1. The whole thing is U1. And your resultant would be VR1. Relative velocity of the air with respect to the blade would be VR1, and that makes an angle theta. And V1 when is resolved in flow, this is the VF1 axial direction, and the whirl component is VW1. So this would be U1 minus VW1. Okay. Now
direction
air
direction.
Inlet velocity of the air.
Like air like
axial entry. Axial turbine.
Clear sir. Like like usually water jet air based compressor inlet compare clear
This is the axial direction. Okay. If I go into the picture, this is your axial direction. Okay. And the cursor it moves from left to right. So you can see the tip. It hits one end of the tip, it goes to the other end. It hits at this end, then goes to the other end. അതാണ് ഞാൻ ഇവിടെ കാണിച്ചേക്കുന്നത്. This is it hits at one end, then goes to the other end. ഇത് സ്റ്റേറ്റർ ബ്ലേഡാണ് ഈ മേൾ സെറ്റ്. സ്റ്റേറ്റർ അല്ല, റോട്ടർ ബ്ലേഡ്. ഇത് സ്റ്റേഷനറി ബ്ലേഡ് താഴെ ഇരിക്കുന്നത്. രണ്ട് എയറോഫോയിലാണ്. അപ്പോൾ ഇവിടെ വന്ന് ഹിറ്റ് ചെയ്യും ആക്സിയലി. And that is hitting at an angle alpha with the axial direction. So it hits at axial direction, but the blade is moving U1 at this end. So it is moving like this. So you have a resultant VR1. This V1 is split into VF1 and VW1. And that will be gliding over this aerofoil, and it will be going out in the same VR2 you will get here. Confusion Mario?
Sir,
okay. Imagine ചെയ്യാനുള്ള പാടാ. Okay, so it glides over this. So you know that VR1 because of the geometry and all, VR1 is actually not equal to VR2. Not in other cases where we have taken this as same. VR1 is not equal to VR2. So once you take this as VR2, whatever it is coming out, so that is making an angle phi with this axial direction. Okay. Now this tip is moving with an velocity u2, that end, because the direction of this direction. So u2 it makes. So what is the actual absolute velocity is nothing but in this direction. So that is v2, and v2 makes beta with the axis of the rotor, the beta. So this v2, if you resolve into flow component and work component, you will get this as vf2, and this part is vw2. Outlet velocity triangle. നിങ്ങൾ എന്തെങ്കിലും അഭിപ്രായം പറയൂ.
Okay, sir.
Okay. So basically we can see that they almost look the same. This is V1, this is V2, this is VR1, this is VR2. The whole thing is, this is U2, the whole thing is U1. The center one is VF1, and this is VW1 and VW2. Okay. All right. ഇത് വരച്ചെടുക്കണോ, അതോ ഞാനിത് അയച്ചു തന്നാൽ മതിയോ? കേട്ടില്ല.
ഇച്ചിരി വരച്ച് കാണിക്കാൻ പറ്റുമോ? ചിലപ്പോ കൺഫ്യൂഷൻ ഇച്ചിരി ഒഴിവായി കിട്ടും.
ഇതിനകത്ത് വരച്ച് കാണിക്കാനോ
പറ്റുമോ?
ഇതിനകത്ത് എങ്ങാണ്ട് ഒരു വൈറ്റ് ബോർഡ് ഉണ്ട്. എൻ്റെ വൈറ്റ് ബോർഡ് ഓപ്പൺ ആയോ? ഓപ്പൺ ആയോ? കാണാം നമുക്ക്? ഇല്ലല്ലേ? നോക്കട്ടെ. കാണാമോ? ഇല്ല.
സർ ജാംബോർഡ് എന്നിട്ടൊരു ലിങ്ക് വന്നിട്ടുണ്ടായിരുന്നു.
ഏതാണ്?
ജാംബോർഡ് എന്ന് പറഞ്ഞിട്ട് സർ
അത്
അതില്
ക്ലിക്ക് ചെയ്ത് നോക്കി.
ആ സർ ഒരു മിനിറ്റ്.
കാണാം.
ആക്ച്വലി സാർ ഞാൻ മൊബൈലിൽ നിന്നാണ് കയറിയിരിക്കുന്നത്, അപ്പോൾ ആപ്പ് ഡൗൺലോഡ് ചെയ്തുകൊണ്ടിരിക്കുക.
നോക്കട്ടെ. ആ ഓക്കെ, ഇപ്പോൾ വന്നോ?
സാർ
വന്നോ?
ആ സർ ഇപ്പോൾ വന്നു.
ഓക്കെ. എനിക്ക് പേപ്പറിൽ തന്നെ എഴുതാൻ വലിയ പാടാണ്. എന്നാ നീ മൗസും ഇല്ലാതെ തന്നെ കൊണ്ട് ടച്ച് പാഡിൽ കൂടെ എഴുതിയിരിക്കുന്നത്. ശരി. ഓക്കെ, സോ ദിസ് ഈസ് ദ ബ്ലേഡ്. ഓക്കെ, so you have air coming in this direction. So this is your V1. Okay, this V1 is making with the axis of rotation alpha. This is alpha. Okay, this is alpha, but this blade is moving in u1 velocity, moving in u1. Now I wanted to find out what is the resultant. So what I'll do is I'll not draw it here. I'll draw this u1 here, v1, not u1, v1. So this is my v1. I just shifted it from here to here, the u1. So together if I take it, then this is my relative, the velocity of air with respect to the blade. So this is my vr1, vr1. Now if this is the v1, then if I resolve it into the flow direction and the drill component, so this would be my vf1, then this would be my vw1, this would be my this alpha, and this would be my this relative velocity component be my theta. Okay.
Yes, sir. Yes, sir.
മനസ്സിലായോ? ഇനി ഞാൻ അടുത്ത വരയ്ക്കട്ടെ.
Yes, sir.
കേൾക്കുന്നില്ല, ഉറക്കെ പറ. സംശയമുണ്ടോ? ഇത് മായ്ച്ചിട്ട് എടുത്ത് വരയ്ക്കാൻ പറ്റുമോ എനിക്ക്?
മനസ്സിലായി സർ.
Okay. Now this VR1 will be flowing over the blade, and it reaches the other end. Okay, it reaches the other end. So if I draw the blade, so this is the blade. So this end it goes out like this. Say this would be my VR2, and but the blade is moving with some velocity at this end u2. So I have just drawn that u2 here. That is u2. That is u2. Then combine this. That would be my absolute velocity, actual velocity of the air. So that is v2. So if I resolve this v2 into the flow component, this would be my vf2, vf2, and this part would be my VW2. And this angle would be my beta, because the opposite one is alpha, and this would be phi. Right?
Yes, sir.
Okay. Now I'll come back to my PPT. So this is what which is very nicely drawn here. So this is your inlet velocity triangle. So this is V1, this is U1, this is VR1. V1 you are resolving, VF1, and this is VW1. This is gliding over this. It comes here. It comes on VR2. So the end is moving with U2. That is U2. So if you take the together, you will get V2 as this. V2 is resolved into VF2 and VW2. So you know alpha, beta, theta, and phi. Okay. Right?
Yes, sir.
Okay. Now you need to note down certain things which are specifically in the case of an air axial flow compressor. One is your U1 and U2, they are the same in other cases also. So U1 is equal to U2 is equal to U. So this length would be same, U1 and U2 for both the ends. The flow velocity through compressor remains a constant. Okay, so your VF1, this VF1 and this VF2, they would be the same. So that is the flow velocity would be the same. This we have seen the graph also, the velocity remains the same. And due to diffusion of the air in the divergent passage formed by the moving blades, there is some pressure rise. Okay, this occurs when the velocity of the air relative to the blade decreases as it passes through the diverging passage of the moving blade. So when it passes through this blade, what actually happens, the relative velocity of the blade actually what you call decreases. Okay, so the relative velocity of VR2 is actually less than your VR1. So this VR1 would be a bigger one as compared to V2. So V2 would be a smaller one because of this diverging passage of the moving plates. Since the work done by rotor is done by the air by the rotor, so the absolute velocity of at the outlet V2 is larger than the absolute velocity of the V1. So V2 is greater than V1. So you can see that this V1 is a small one, but V2 is a bigger one. Okay, because it is imparting some sort of kinetic energy, and this kinetic energy which is imparted is actually what you call it is converted as static pressure energy in the stator blades, so that when it goes from one state to the other, the pressure increases. Okay, so the kinetic energy imparted by the moving blades are converted into pressure energy in the stator blades, and thereby the pressure is increased. And we can compare, we can say that this alpha is equal to beta and this theta is equal to phi. Okay, so this you can, alpha is equal to theta, alpha is equal to theta. These angles are same actually. Okay, from the symmetry. Okay, and beta would be equal to theta. Okay, so these are some of the things that we observe from the velocity triangle of axial compressors. Okay, now how do you find out the work done? Work done is the same thing, change in force is equal to change in momentum. So momentum is mass into the whirl velocity, m into v. So that is m into v w2 minus v w1. You want in terms of power, then it is force into displacement, work done. So displacement is nothing but the u, the velocity u, blade velocity. So that is a displacement. So this is nothing but your Euler equation. the general Euler equation you can directly apply. So M is equal to VW2 U2 minus UW1 U1 VW1 U1. And the mass flow rate M you can find as rho into Q1. Rho because rho and rho 2 would be different because your pressure is different, and the discharge would be correspondingly changing. Okay, so but U2 and U1, because it's a single blade and there is no difference between U1 and U2, you can take it as U. So you can put it as M into VW2 minus U2 into U, and where this is the real component, and this is for a single stage. Okay, similarly, if there are 10 stages, you have to multiply into 10 so that you will get it for the total one, and that is also equal to mcp delta t, or change in enthalpy in terms of stagnation temperature. If you write mcp t02 minus t01, this will be equivalent to this. You can equate. Okay. Now you can further simplify this, because from this triangle you can write tan alpha. Tan alpha is equal to VW1 by VF1. So you want actually VW1. So VW1 you can write as VF1 into tan alpha. Similarly, beta, taking the outlet triangle, you can write it as VW2 into VF2. So that you can write as VF2 into tan beta. So this VW2 and VW1 you can replace as VF1 tan alpha. This is tan beta, and VF1 tan alpha. So this you can replace. That's what you have done here. So this is M into VF2 tan beta minus VF1 tan alpha into U. And Vf1 is equal to Vf2, because we have seen that the flow velocity is the same. So that is Vf. You can take it out. So basically work done can be M into U into Vf, flow velocity, into tan beta minus tan alpha. Okay. So M is mass, U is the velocity of the blade, V is the velocity of flow, into tan beta minus tan alpha, which is the what you call the angle that the absolute velocity makes with the axial direction. Okay, the flow direction into number of stages will give the total input, uh, work input required to compress the fluid. Okay, is it clear?
Yes, sir.
Right. Now, since it is a reaction turbine, we need to find out what is the degree of reaction. You know that degree of reaction is the pressurized in the rotor blade divided by total pressurized in the compressor. Okay, so we calculate that. We have found the pressurized in the rotor blade. We can write in terms of the change in the relative velocity, m into vr2 minus vr1, and the total thing is that we have found now, that is m into v w2 minus dw1. So that ratio if you take, your degree of reaction can be simplified. I can give you a derivation for this after the class, so it can be further simplified, and you can write it as um, uh, Vf into tan square theta minus tan square phi divided by 2u tan beta minus tan u. And if you take the symmetry of the inlet and outer triangles as we have taken earlier, alpha is equal to phi and beta is equal to theta, and it can be further simplified, and it can be written as Vf into tan theta plus tan phi divided by 2u. Okay, and generally for axial for compressor it is 50%. So that means 1 by 2. So this factor is equal to 1 by 2. Then the blade velocity should be Vf into tan theta plus tan phi. So this is a general criteria they follow to find out what is the blade velocity. Okay. So this derivation I will give it to you. You just need to mug up what is the equation. All right. Okay. So you jot down this equations, because we need to solve a problem. So you write what is this equation, that is work input per second, and in terms of VW1, then in terms of flow velocity. So this equation,
Sir, ഈ
ah,
pressure energy ഇല്ലേ,
ah,
അത് യൂഷ്വലി VR2 റിലേറ്റഡ് ആയിട്ടായിരുന്നു എടുക്കുന്നത്. അല്ല, ഐ മീൻ VR1 VR2 റിലേറ്റീവ് വെലോസിറ്റി റിലേറ്റഡ് ആയിരുന്നു. അതെന്തുകൊണ്ട്, അതിന്റെ കാരണം എന്ന് പറഞ്ഞുതരാമോ സാർ?
അത് ആ റോട്ടർ ബ്ലേഡിൽ ചേഞ്ച് വരുന്നത് VR1ഉം VR2 ആയിരിക്കും. റോട്ടർ ബ്ലേഡിൽ ഒരു ഡിഫ്യൂഷൻ സംഭവിക്കും. ഞാൻ നേരത്തെ പറഞ്ഞില്ല, ആ ട്രയാങ്കിൾ വെച്ചിട്ട്. അതായത് ഈ VR1 ഈ ഹയർ റിലേറ്റീവ് വെലോസിറ്റിയിൽ ആക്ച്വലി കയറുന്നത്. പക്ഷേ ഇവിടുത്തെ ഈ ഡിഫ്യൂഷൻ കാരണം ആക്ച്വലി അത് കൺവേർട്ട് ചെയ്യും, പ്രഷറായിട്ട് കൺവേർട്ട് ചെയ്തിട്ട് അതിൻ്റെ റിസൾട്ടൻ എന്ന് പറഞ്ഞാൽ VR2 ചെറുതാവും. നമ്മളിവിടെ പറഞ്ഞു VR2 will be less than VR1. Okay, due to the diffusion of air in the divergent passage formed by the moving blades, there is a decrease as passing through the diverging passages. So ആ സാധനം നമ്മൾ ഈ പ്രഷർ ഡ്രോപ്പ് ഇൻ അക്രോസ് ദ സ്റ്റേറ്റർ ബ്ലേഡ് നമ്മൾ എടുക്കുന്നത് ഈ റിലേറ്റീവ് വെലോസിറ്റിയുടെ ബേസിലാണ്.
ഓക്കെ സാർ.
ഓക്കെ ഓക്കെ, നിങ്ങൾ എഴുതിയെടുത്തോ? അല്ലെങ്കിൽ പ്രിന്റ് സ്ക്രീൻ എടുത്തിട്ടാലും മതി. അതോ നിങ്ങൾ പിന്നെ പോയി പ്രോബ്ലം ചെയ്യുന്നുള്ളോ? ഞാനത് ഷെയർ ചെയ്താൽ മതി, അങ്ങനെ വേണ്ടേ?
ഷെയർ ചെയ്താൽ മതി സാർ.
ഷെയർ ചെയ്താൽ മതി. ഓക്കെ ഓക്കെ. So you will get the degree of reaction, yeah, as VF into. This is a problem. An axial flow turbine having 8 stages. You can see that there are 8 stages. 50% degree of reaction. It compresses air to a pressure ratio of 4. Inlet conditions given. Airflow through the compressor at constant velocity 90 meter per second. Mean speed of the rotor blade is 180 meters per second. Isentropic efficiency of the compressor is given. Okay, so the whole thing you have to multiply with this inefficiency 0.82 so that you can solve it. Okay, you have to find out what is the work done and also the blade angle. So you need to draw the velocity triangle and solve it. Okay, I'll share this with the solution. Then സംശയം ഉണ്ടെങ്കിൽ ചോദിച്ചാൽ മതി പിന്നെ. Okay, right?
Yes sir.
Now another parameter that we have to learn in this one is the flow coefficient, again for axial flow compressor. So it is the axial flow velocity divided by the tangential blade velocity. Axial flow velocity divided by the tangential blade velocity. So that is VF, that is axial flow, divided by the tangential blade velocity is U. This we can write in terms of degree of reaction. From there, you take it as 0.5 and you will find your U as this. So that you will replace here. So you divide. So you will get it as 1 by tan theta plus tan phi. And again, if you simplify, this can be again written in terms of alpha and beta. Then it will be 1 by tan beta plus tan phi. Okay, so it's called the flow coefficient. They may ask in question, find out the flow coefficient. You should know that what by what and what is the equation. Okay, need to by heart this. Then there is a third one which is called the work coefficient or the head coefficient. It is actually the actual work done on the air divided by kinetic energy corresponding to the mean peripheral velocity of the blade. Okay, so that is in terms of half mv square kinetic energy, and this you take it as MCP, temperature change. So this ratio, if we take, it is called the work coefficient or the head coefficient. Okay, so yeah, this is also asked. So don't get confused with flow coefficient, pressure coefficient, and work coefficient. They are different. Okay. Pressure coefficient is isentropic work on the air divided by kinetic energy. So kinetic energy is corresponding to the peripheral velocity. So you can have isentropic efficiency is the same efficiency that we have discussed ഇവിടെ ഞാനൊരു പടം ഇട്ടെന്നേ ഉള്ളൂ. ഇതൊരു 8 അല്ല, ഇവിടെ 2 ആണ്. So this is the normal compression, this is the isentropic compression, this is the actual compression. So this by this would be a efficiency of the turbine. So T2 dash by T1, the 2 alla 8 alla 2 dash ആണ്. So T2 dash minus T1, and this is T2 minus T1, which is the actual one. So this ratio, if you take, multiply that, then it is your isentropic work done into efficiency if you can put in there. Okay, and the kinetic energy or mean kinetic energy according to the blade velocity is half mv square. So this ratio, if you take, what you get is the pressure coefficient. So mcp, isentropic efficiency, into T2 minus T1, which is the actual temperature change, divided by half. So you will get it as nothing but your head coefficient, eta, or the work coefficient. So we can make this equation, eta pressure coefficient is equal to isentropic efficiency into head coefficient. Okay, some mathematical terms that you should know. Okay, okay, this is a problem where you need to find out the number of stages and also the flow velocity of flow. Okay, a simple problem. For this also I'll give you the solution. This is a typical problem that can be asked. Okay, an axial flow compressor, 50% reaction, has a blade outlet angle of 35 degree. Flow velocity is 0.5 times the mean blade velocity. Speed of the rotor is 800 rpm. Stagnation, from there you can find what is the blade velocity. Stagnation condition at the entry is 1.6, that is the inlet condition, 10 centimeter, and the static pressure in this thing is 0.95 bar. Draw the velocity triangle and find the power required. Mass flow rate, mean diameter, flow area is given, mean square. Okay, so we can find out what is the velocity triangle and the power required, mass flow rate, and things like that. Okay, so these things I'll give you the solution. You go through that and come back to me if you have some doubts. Okay, this is also another way to find out what is the blade angles. Okay, all right, some questions? Yes. This is about axial flow compressor. I hope you have gotten some idea. More or less the same what we have studied earlier, like any reaction type, centrifugal compressor type thing. Have you started studying?
Yes, sir.
Okay. Okay, go through this. ഇത് ഞാൻ ആർക്കെങ്കിലും മെയിൽ ചെയ്ത് തരാൻ പറ്റുമോ? ആരെങ്കിലും ഒരാളുടെ മെയിൽ ഐ ഡി പറഞ്ഞേ. ആരുടെ മെയിൽ ഐ ഡി ഇല്ലേ?
സർ ചാറ്റിലിട്ടു സർ.
എന്താണ്?
ചാറ്റിലിട്ടു സർ.
ചാറ്റിലിട്ടോ? ഓക്കെ. Chat. Okay.
സർ, ഈ സ്റ്റെബിലിറ്റി ലൂപ്പിനെ പറ്റി ഒന്ന് പറയാമോ?
ഏതാണ്
സ്റ്റെബിലിറ്റി ലൂപ്പ്?
സ്റ്റെബിലിറ്റി ലൂപ്പോ? എവിടെ ചോദിച്ചേക്കുന്നത്? എന്ത് ചോദിച്ചേക്കുന്നത് സ്റ്റെബിലിറ്റി ലൂപ്പിനെ കുറിച്ച്?
അല്ല, ഗ്യാസ് ടർബൈൻ്റെ സിലബസിലുള്ള ലാസ്റ്റ് പോർഷൻ.
അതിൽ ചോദ്യം വന്നിട്ടുണ്ടോ?
ഇല്ല, ചോദ്യം വന്നിട്ടില്ല. അതില് സ്റ്റെബിലിറ്റി ലൂപ്പ് നമ്മൾ നെറ്റിൽ നോക്കുമ്പോൾ ഒരു ഗ്രാഫ് ഒക്കെ കൊടുത്തിട്ടുണ്ട്, വീക്ക് ലിമിറ്റും റിച്ച് ലിമിറ്റ് എന്ന് പറഞ്ഞ എയർ ഫ്യൂൽ റേഷ്യോ വെച്ചിട്ടുള്ള.
ബേസിക്കലി അതൊരു കമ്പഷൻ്റെ സാധനമാണ്. അതായത് ഈ ഒരു ലിമിറ്റിംഗ് എയർ ഫ്യൂൽ റേഷ്യോ നിങ്ങൾക്ക് അറിയാമല്ലോ അല്ലേ? കമ്പഷനകത്ത് അറിയോ എയർ ഫ്യൂൽ റേഷ്യോ? സ്റ്റോഷിയോമെട്രിക്കലി കറക്റ്റ് എയർ ഫ്യൂൽ റേഷ്യോ അതൊക്കെ അറിയാം?
അതറിയില്ല സർ.
അതായത് എനി കമ്പഷൻ പ്രോസസ് ഒത്തിരി നമ്മൾ ഫ്യൂവൽ കൂട്ടി കഴിഞ്ഞാൽ കൂടുതൽ എനർജി കിട്ടുന്നൊരു തെറ്റായ ധാരണയുണ്ട്. യു വിൽ നോട്ട് ഗെറ്റ് ഇറ്റ്. ഓക്കെ, ദർ ഈസ് എ സ്റ്റോഷിയോമെട്രിക്കലി മീൻ കെമിക്കലി that this much molecules of fuel and this much molecules of air react to produce. So there is a balanced chemical equation which is there. Okay, അപ്പം അതാണ് സ്റ്റോഷിയോമെട്രിക്കലി കറക്റ്റ് എയർ ഫ്യൂവൽ റേഷ്യോ. ഓക്കെ, അപ്പം അതിൻ്റെ താഴെ ഒരു സാധനം ചെയ്ത് കഴിഞ്ഞാൽ നമ്മൾ പറയും ലീൻ മിക്സ്ചർ എന്ന് പറയും, വേർ ദ ഫ്യൂവൽ എമൗണ്ട് ഈസ് ലെസ്. അതിൻ്റെ മേളിലാണെങ്കിൽ റിച്ച് മിക്സ്ചർ എന്ന് പറയും. സോ ദ ഫ്യൂവൽ എമൗണ്ട് ഇസ് മോർ. സോ ഡിപ്പെൻഡിങ് അപ്പോൺ വാട്ട് ഈസ് ദ റിക്വയർമെൻറ്റ്, the modern intelligent vehicles have got a program which will determine whether it should be rich at some time, it should be lean. It generally is not at stoichiometrically correct air fuel ratio. Okay, there are a lot of what you call things that happens. Okay, അപ്പോൾ അതിന് ഒരു റീജിയൻ ഉണ്ട്. There is a region with which this can happen. അപ്പം വീക്ക് തുടങ്ങുന്ന ഒരു ലിമിറ്റ് പോലെ നമുക്ക് വെക്കാം, റിച്ച് തുടങ്ങുന്ന ഒരു ലിമിറ്റ് പോലെ നമുക്ക് വെക്കാം. സോ ഇൻ ബിറ്റ്വീൻ ഇഫ് യു ഓപ്പറേറ്റ്, യു ആർ ഇൻ എ മോർ what you call a stable region. They call stable or a what you call an efficient region. Okay, above that if you go it is not good, below that if you go. So but this is again a factor. If you come into what you call this gas turbine and all, and the mass flow rate of the air, and when mass flow rate is varied, this air fuel ratio also varies accordingly. Okay, how much it should be. So there is actually a region where you can operate. Okay, that is sometimes called as your stability loop. Okay, so it's a range between rich and weak limits. They say the rich area and the weak area. If air fuel ratio is reduced, 50, 100, 150, ഇതാണ് യൂഷ്വലി എയർ ഫ്യൂൽ റേഷ്യോ. അതിൽ താഴോട്ട് പോവുകയാണെങ്കിൽ ഇറ്റ് ബിക്കംസ് മോർ റിച്ചർ. മേലോട്ട് നമ്പർ കൂടുകയാണെങ്കിൽ ഇറ്റ് ഈസ് മോർ ഓഫ് എയർ. ഓക്കെ, മോർ ഓഫ് എയർ, ഫ്യൂവൽ ഇസ് ലെസ്. ഓക്കെ, സോ അക്കോർഡിംഗ്ലി യുവർ ദിസ് തിങ് ചേഞ്ചസ്. അപ്പം ഒത്തിരി അങ്ങ് ലിമിറ്റ്, അപ്പോൾ ദർ ഈസ് സംതിങ് കോൾഡ് കമ്പഷൻ ഇൻസ്റ്റബിലിറ്റി. ചിലപ്പോൾ അതങ്ങ് അണഞ്ഞു പോവും, ഫ്ലെയിം അണഞ്ഞു പോവാം. Then there are other issues like combustion instability and all, waves ഒക്കെ ഫോം ചെയ്യാം. So you don't want to get into that trouble where the whole system becomes unstable. ഈ റോക്കറ്റ്സിനകത്തൊക്കെ ഇത് വലിയ ഇഷ്യൂസ് ആണ് ഈ കമ്പഷൻ ഇൻസ്റ്റബിലിറ്റി. So you have to basically what you call make sure that it is within that stability limits. And again there are other parameters like your temperature, pressure and all which affects. So ഇതെല്ലാം വെച്ചിട്ട് നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്യുന്ന ഒരു റീജിയൻ ആണ് സ്റ്റെബിലിറ്റി ലൂപ്പ് എന്ന് പറയുന്നത്. നിങ്ങൾക്ക് അതിന് ഡോക്യുമെന്റ് എന്തെങ്കിലും വേണോ? ഞാൻ നോക്കട്ടെ, അതിനകത്ത് ഇടാൻ പറ്റുമോ നോക്കട്ടെ. സ്റ്റെബിലിറ്റി ലൂപ്പിന്റെ ഒരു ഡോക്യുമെന്റ് ഞാൻ ഇടാം. ഇത് ചെറിയ റൈറ്റപ്പ് എഴുതിയാൽ മതിയാവും അല്ലേ? ഷോർട്ട് നോട്ടാണ് ചോദിച്ചേക്കുന്നത്.
സിലബസിൽ ജസ്റ്റ് മെൻഷൻ ചെയ്തിട്ടുണ്ട്.
ശരി 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 അത് ഞാൻ ഇട്ടേക്കാം, ഈ PPTക്ക് ഇട്ടേക്കാം.
Thank you, sir.
എനിത്തിങ് എൽസ്? നിങ്ങളുടെ പിയർ ലേണിംഗ് ഒക്കെ നടക്കുന്നതിനോട് കൃഷ്ണകുമാർ സാർ പറഞ്ഞു.
ചെറുതായിട്ട് നടക്കും.
ഓക്കെ. കാരണം ചില കാര്യങ്ങൾ ചിലർക്ക് പെട്ടെന്ന് മനസ്സിലാവും, ചില കാര്യങ്ങൾക്ക് ചിലർക്ക് താമസിച്ച് മനസ്സിലാകത്തുള്ളൂ. അപ്പോൾ അങ്ങോട്ടും ഇങ്ങോട്ടും നിങ്ങൾ ഇത് ചെയ്യുവാണെങ്കിൽ ഇറ്റ്സ് ഗുഡ്. ഓക്കെ, ഇറ്റ്സ് എ ഗുഡ് അപ്രോച്ച്. രണ്ടുപേരുടെയും സമയം സേവ് ചെയ്യാം. ഓക്കെ, എനിത്തിങ് എൽസ്?
ഇല്ല സർ.
ഓക്കെ, അപ്പം ഞാനിത് അയച്ചു കൊടുത്തേക്കാം. ഇത് ആരുടെ? റോയ്സൻ്റെ ആണ് ഇട്ടേക്കുന്നത്?
ആ സർ.
ഓക്കെ, ഞാനത് ഷെയർ ചെയ്തേക്കാം.